The universe holds many mysteries: dark matter, black holes, and even why some people wear socks with sandals. But perhaps the biggest mystery of all is antimatter. During the Big Bang, equal amounts of matter and antimatter should have been created. Instead, we have a universe full of matter with only faint traces of its counterpart. So where did all the antimatter go? Let's dive into the video. The birth of a cosmic rivalry. Matter versus antimatter. During the universe's inception, equal amounts of matter and antimatter were supposed to be created according to the laws of particle physics, particularly the Standard Model. However, the matter-antimatter asymmetry implies that the laws of physics must contain a slight preference for matter. Current research focuses on understanding the imbalance through various means, including investigating subatomic particles like quarks and leptons. CP violation, which involves differences in the behavior of particles and their antiparticles, is considered one possible explanation. Experiments conducted by collaborations such as Bell 2 in Japan and Large Hadron Collider at European Organization for Nuclear Research aim to measure CP violation more accurately to understand its role in this imbalance. The ghost particles and neutrino mysteries. Neutrinos are among the most enigmatic particles in the universe and have very small masses, which allows them to travel at nearly the speed of light. In recent years, the T2K experiment in Japan has been able to measure neutrino oscillations with a high degree of precision. These measurements suggest that there could be tiny differences in the oscillation rates of neutrinos and antineutrinos. If confirmed, this disparity might indicate CP violation in neutrinos, providing an important clue as to why matter prevailed after the Big Bang. Additionally, the Deep Underground Neutrino experiment in the United States aims to further investigate this phenomenon by comparing neutrino and antineutrino behaviors over long distances. CERN's Large Hadron Collider beauty experiment and symmetry violations. The Large Hadron Collider at CERN has allowed scientists to study a phenomenon called charge parity violation, which refers to differences in behavior between matter and antimatter. Charge parity violation has already been observed in certain subatomic particles called cons and B mesons, providing direct evidence that matter and antimatter are not perfect mirrors of each other. The Large Hadron Collider beauty experiment focuses on these types of particles to understand these differences in greater detail, and results from these studies could help explain why our universe has so much matter and almost no antimatter. Alpha magnetic spectrometer. A cosmic antimatter hunter. The alpha magnetic spectrometer was designed to look for traces of antimatter in the form of cosmic rays from potential antigalaxies. Since its launch in 2011 aboard the International Space Station, Alpha Magnetic Spectrometer has provided insights into cosmic rays, but has not found any definitive signs of antistars or antigalaxies. This supports the hypothesis that antimatter might be very rare in the universe, though some scientists argue that more data is needed before drawing firm conclusions. Nobel Prize winner Samuel Ting, who leads the AMS project, has emphasized that continuing this search is crucial, as a confirmed detection of antimatter from an antigalaxy would revolutionize our understanding of the cosmos. Antistars. Maybe antimatter isn't missing, it's just shy. Scientists have proposed the possibility of antistars, hypothetical stars made entirely of antimatter. Observing such stars would provide direct evidence that antimatter still exists in significant quantities elsewhere in the universe. Researchers using the Fermi Gamma Ray Space Telescope have attempted to identify gamma rays resulting from interactions between matter and antimatter at these distant stars. The absence of these gamma rays suggests that if antistars do exist, they are either extremely rare or located far beyond our observational capabilities, making them challenging to detect with current technology. Could a cosmic mirror universe exist? The idea of a mirror universe is linked to theories of symmetry and parallel realities. In cosmology, the idea suggests that the universe split into two distinct realms during the Big Bang, one dominated by matter and the other by antimatter. Theories involving multiverses, including the concept of mirror universes, are often used to explain anomalies in quantum mechanics and the missing antimatter problem. Such a parallel universe would be almost impossible to detect with our current instruments, but ongoing advances in quantum physics and high-energy experiments may provide new ways to investigate this tantalizing possibility. Nobel Prize controversies and antimatter's elusiveness. Samuel Ting's views on antimatter research reflect the broader challenges faced by scientists trying to reconcile theory with observation. The AMS experiment continues to collect data, with its latest results hinting at some unexplained excess in cosmic positrons, the antimatter counterpart of electrons. This suggests that there could be sources of antimatter that we have not yet understood. Other scientists have suggested that dark matter interactions might explain these findings, though it remains a subject of ongoing debate. The disagreement on whether antimatter is truly missing or simply undetectable highlights the limitations of current observational methods. The role of particle colliders in solving the mystery. Particle colliders like the Large Hadron Collider recreate conditions similar to those that existed fractions of a second after the Big Bang. These high-energy collisions allow scientists to study matter and antimatter production directly. Experiments have shown that certain particles, like B mesons, exhibit CP violation, which is a necessary condition for creating the observed matter-antimatter imbalance. The insights gained from colliders complement other experiments focusing on neutrinos and cosmic rays, creating a more comprehensive approach to tackling the antimatter mystery. The future upgrade of the LHC to the High-Luminosity Large Hadron Collider is expected to provide even more precise data to further understand these subtle imbalances. Is dark matter the antimatter's evil cousin? Some theories suggest that dark matter, an invisible form of matter that interacts only through gravity, could be related to the disappearance of antimatter. It is possible that during the early universe, interactions between antimatter and dark matter could have led to the current imbalance. Research into weakly interacting massive particles, a leading candidate for dark matter, is being conducted using detectors like the Xenon 1T experiment. These detectors aim to catch rare collisions between dark matter particles and atomic nuclei, which might also give clues about their interaction with antimatter. While results so far have not confirmed any such interactions, the search continues with newer and more sensitive instruments. The ongoing hunt. Don't give up yet. The hunt for antimatter is an ongoing global effort. Future projects, such as the Hypercamiocand in Japan, will expand on neutrino research to further investigate potential differences between matter and antimatter. Additionally, the Einstein telescope, a next-generation gravitational wave detector, could potentially detect faint signals from antimatter interactions, giving us a new way to probe this mystery. The European Space Agency is also considering missions that could provide a clearer picture of cosmic ray origins. All these efforts are aimed at answering fundamental questions about the early universe, the forces that shaped it, and why we exist in a universe dominated by matter rather than being a void of annihilated particles. Thanks for joining me on this journey through the fascinating world of antimatter. If you found this video insightful, please give it a like and hit that subscribe button and ring the bell icon so you're notified whenever we post new videos. Stay curious, and I'll see you in the next one.